everyone and welcome to a new discussion which we are going to have in the series that is number 10. In earlier discussion, just in previous discussion rather, we have discussed what are the geological ways of groundwater explorations. That means the geological techniques which we apply starting from survey and even from cross section and other things. But sometimes what happens when your geological methods are not yielding, or the mapping which we have done or cross section which we have prepared of how about an area are not yielding any good results about the position of aquifer and thickness and worthiness of an area from groundwater resource point of view, then we resort to the next stage, that is involving geophysical methods. Or rather initially I would call surface geophysical methods, and later on we will also discuss what are the subsurface geophysical methods as well. So, for subsurface, of course, for geophysical methods we have to have a borehole or a drill well, and then instruments are lowered in that drill well, and then data is collected. But that is a very, I would say, expensive, and that is the last resort to know the subsurface geology or subsurface arrangement of aquifers, confined and unconfined, impervious and pervious layers, etc. So, basically here first here is then when we are not getting good information from geological methods, then we resort to the surface geophysical methods, or maybe in this we might be going for some exploratory drilling, not exactly I would say test drilling, but exploratory drilling, which is not sometimes very deep, but initially we would like to know what is near surface geology is. So, sometimes also that geophysical surveys, such kind of surface geophysical methods when we apply for groundwater exploration may be relatively quick and as compared to even geological methods, and inexpensive to gain subsurface information. Why? Because there are electrical methods which we will be of course discussing just after this discussion, and that electrical methods instruments are sometimes not very expensive, and a quite good area can be covered in a very quick manner, and a lot of information related with groundwater, aquifers and other things can be obtained to some accuracy. So, therefore, it is mentioned that relatively quick and inexpensive in relative sense. And these surface geophysical methods exploit basically the physical properties, characteristics and parameters of geology or rocks or layers which are present. For example, we try to exploit through these methods about the density, electrical conductivity, and electrical conductivity vary rock to rock, which we will be also discussing. Electrical conductivity varies with the moisture content or saturation of water, and also electrical conductivity get influenced because of salinity in the water. So, electrical conductivity or this resistivity methods are very useful in case of groundwater exploration, where we involve the geophysical methods. Then we are having also we can have a potential and magnetic susceptibility information, and we can also involve to some extent radioactivity and elasticity of the rocks which are present to know what kind of aquifer conditions are there in subsurface. So, these are the methods or properties, characteristics which we are exploited through such kind of surveys. So, these characteristics, as I have just mentioned, that like example of water and salinity, many of these characteristics of aquifer or rock formations layers are influenced by presence of water and salinity also. And as we know that the success of geophysical methods basically will depend how best the physical parameters are deduced, interpreted in terms of presence of groundwater or in terms of hydrogeological features. And another important thing is that once we are having geological information, based on that we can also decide that which geophysical or surface geophysical methods would be more appropriate, most appropriate for that particular area. What I am trying to say that everywhere we cannot go blindly for just resistivity surveys and say that things can be done. If it is a hard rock terrain, then sometimes resistivity survey will not yield very good information about subsurface geology. So, therefore, geological methods will always remain the first step in this direction for groundwater exploration, but that will also support that which geophysical method should be adopted first to get the or deduce the hydrogeological features. Further, geophysical characteristics or their range for different rocks are not unique, means there are no standard values. So, we will have the ranges of, and sometimes these ranges of these geophysical characteristics of rocks or formations is quite wide, which we will see through a table. So, these are not unique to hydrological parameters. Basically, as I have been saying earlier also, I would repeat that part here also, that each and every part of this earth is unique by itself. When on surface we are having unique lithology or geology, then on subsurface also we are having. So, on one place if we are getting a sequence of rocks or aquifers, confined aquifers, but maybe after 3-4 kilometers we may not be having exactly the same arrangements of rocks or aquifers. So, therefore, there are ranges of all these characteristics which we will see, and how these ranges are influenced by presence of water and salinity. And more alternative arise from which a choice has to be made on the basis of hydrogeology of the area. So, that part has to be explored first, and then the choices are available for choosing a best appropriate method, or when after even looking through the ranges of these geophysical characteristics, appropriate geophysical technique, surface geophysical technique can be adopted. So, sometimes we have to say we first start with resistivity method, and if we still we are not yielding good results, but the requirement of water is there or exploration is very much required, then we may go for another method. So, combination of 1 or 2 or 3 methods of geophysical surveys can be adopted for one single area, and this happens only in those areas where there is a problem of getting water. Areas which like Indo-Gangetic plain, there are much of this area is having water at certain depth, or varies, of course the depth varies area to area, but still we know that water will be available. But there are areas where water is a big problem, so where we might go for 1 or 2 or 3 methods for groundwater exploration. Now, this as we have briefly understood that the main prime objectives of geophysical surveys are to provide information on depth, thickness, extent of aquifers in a stratified formation. When we say stratified formation, it does not mean that we are only talking about sedimentary rocks. Stratified formations may be a igneous terrain where the top part is weathered, fractured, the lower part might be a full solid rock. So, there are 2 strata basically, 2 strata or 2 loosely we can say 2 formations, one is the weathered one, another one is a consolidated one. So, that is why this term is used as stratified. Similarly, in case of metamorphic terrain, similar things can also happen. So, it is a in a very generalized manner this word is used, stratified formation. Again I am saying it does not mean that we are only talking about sedimentary terrain. So, depth, thickness and extent of aquifers can be estimated using surface geophysical methods. Another aim of such methods are the depth, thickness and extent of weathered and fractured zones and massive rocks. This is typical in igneous and metamorphic terrain. So, similarly, when we are looking in sedimentary rocks, we are looking also water in the igneous and metamorphic terrain. Depth to water table, of course, this is another very important, where we will get the water table. So, what would be the depth of our potential or future bore well and so on and so forth. So, that kind of information is also acquired through such surveys. Structural and stratigraphic conditions controlling the occurrence of groundwater. That means that what are the structural features which are present, which can be also interpreted or deduced from these surveys data. and and also stratigraphic conditions. What are the sequence of rocks starting from bottom to top? Whatever the depth, from depth up to which depth these surveys are giving information, and from starting from that depth you will come to top. So, if it is a igneous terrain, then we will be getting a one zone which is a weathered and fractured zone, another one we will be getting a massive rocks. So, that kind of stratigraphic conditions, but it is more this term is more used for sedimentary and other rocks as per their age. And another important thing, as we know that the geophysical characteristics of rocks are influenced by water and salinity present. So, therefore, these surveys will also give us about the salinity distribution, pollution in the water and contamination, if at all it is there. In many cases that might be a problem. So, that kind of information can also be given. And potentials of aquifers, what kind of aquifers are there and what are the potentials of those aquifers, how much water will yield through our wells and so forth. And of course, the movement of groundwater, how water flows from one place to another, that kind of information can also be extracted or interpreted from geophysical data, which will come through our different geophysical surveys. Now, here only principles of geophysical methods are described. So, we are only discussing the main methods or only the principles, the basic things about the these methods are. So, this detailed description, if somebody is looking and their applications about the geophysical methods and interpretation techniques, then there are a lot of literature books are there. So, for that it can be referred, because this course is for groundwater engineering. So, only there is a limited scope for like for geological methods, similarly limited scope for geophysical methods, and similarly we will have a limited scope for subsurface geophysical methods. So, that is why I have said that those who are more interested can refer to dedicated literature. Lot of literatures are already available. Now, the first method which we will take here is the electrical method. So, which depends on one of the characteristics of rocks, which is electrical conductivity. If water is present, salinity is present, then of course, the electrical conductivity or resistivity will be influenced with that. So, electrical prospecting or electrical methods use a variety of techniques. Two main techniques which we will be discussing in this discussion, which are based on the electrical resistivity. It is a most common technique, surface geophysical technique for groundwater exploration. As said in the beginning in this discussion, that perhaps this is the most cost effective as compared to other geophysical techniques. That is why it is more commonly used. So, the context between certain lithological units and between water saturated and dry formations. That means, we will be getting a water table between the saturated at the bottom and dry formation on the top, and the zones of different salinity can be identified based on this resistivity methods. Because from the contrast which we will be getting in the resistivity of different formations, stratified from formations or formations in sequence and other thing. So, in that way the contrast is being looked through this method about the electrical resistivity of different materials, rocks, soils, or saturated with water with salinity is there. And so, for example, if we take a quick example here, then dense impervious rocks have high resistivity, and vice versa will also be true, that porous and pervious rocks will have low resistivity. That means, there are chances of getting moisture inside those porous medium and also water. If water is there, of course, the conductivity would be high, resistivity would be less, say reverse relation. So, in general, lower resistivity indicates water saturated and having salinity. Now, here these are the common rocks and their resistivity, minerals and waters are shown here. The resistivities of common rocks, minerals and water. We know that there are all kinds of rocks are there. So, that we cannot have a exhaustive table, and so very common rocks which we will be seeing, and also the minerals which are sometimes are encountered in among as formations, and of course, the water saturated or not. So, if we see that the water which is potable, which is used by for drinking and irrigation, that water resistivity ohm meter, that would be 10 to 100 ohm meter. And whereas in brine water it is going to be quite less, 5 multiplied by 10 to power minus 2. And if we see the gravel sand, and which is in case of dry, and one is the saturated with water, and see that this will have, the dry will have several thousands ohm meter, and whereas once it is saturated with water, then it will have just 15 to 600 range, depending on type of sediments, how they are, what rocks or what minerals they are formed, and what are the sorting and other things. So, that is why a big range is given. What I am trying to say, that in some case if we find a gravel and sand sediment saturated with water, we cannot say without testing that it is having a 15 ohm or 600 ohm. It has to be tested, but normally we will get the range of ohm meter between these 15 to 600. Now, when we come to the typical rocks like limestone, it will have 10 to power 3, the resistivity is quite high. In crystalline rocks, it is further high, it is 10 to power 6. Crystalline rocks would of course include sedimentary rocks, and consolidated sedimentary rocks means sedimentary rocks which are quite hard, maybe sandstone or more quartzitic sandstone kind of situation. Then we will have a electrical resistivity around 10 to so, here the range is not much, but still would be there. If we are getting just quartz layers or formations which are very rich in silica, or we are having quartz reefs or something like that, then it is very high, resistivity is 10 to power 11. And then calcite, which is again calcium carbonate, and it is 5 multiplied by 10 to 12, again. So, the resistivity is very high. So, that kind of ranges are available, people have understood through experiments, and a similar kind of tables have been made. So, this table will give you some idea if at all you are doing such a surveys. So, this table will give you idea if you are having information about different types of formations which are present, it will give you idea that what kind of resistivity range you would be encountering. Now, we will look how exactly these surveys are done. I mentioned that there are two methods two methods for arranging these electrodes which are present here. So, let me first explain. This is the line which we are seeing is the ground surface, a thick black line running horizontal. Then there are electrodes A and B, and at there are two more electrodes in between, one is M and N. So, what is being done, that through a battery source in the field, because that is the main source available, and all other instruments will also work at say 12 volt or 24 volt. So, through a battery source, a current is sent to these two poles, and there is of course current meter is also installed, or ammeter you can say. Then between M and N, the potential difference between this current is measured through a voltmeter which you are seeing. So, let me repeat very quickly. We are having a ground surface shown here as a thick line. You are having 4 electrodes. First electrode is A and second electrode is B, through which the current is passed to the ground, and through electrode M and N, the potential difference between these currents which is received by these is measured through a voltmeter, and that will give you the idea how the currents are flowing. As you can see, the arrow very clearly indicates. Further, you would see if the distance is more between A and B, then the depth or these contours which are shown in the red color with arrow will go much deeper and deeper. However, the signals which will come in the M and N electrodes or this voltmeter would be very less. So, there are always optimization that we should not put a distance between A and B to kilometers, but just few meters, and there are some depending on again subsurface geological conditions. So, based on that some experience, people try to keep that distance, and there are also arrangements how these electrodes are arranged. Here what we are seeing, they are arranged So, distance between A and M is the same as M and N and B is also same. So, here at the same distance the current electrodes and the bolt electrodes or potential difference electrodes are there. So, current voltage is here, the flows are there, and this is one of the schematic of how the electrical surveys are done, employing two different methods, Wenner and Schlumberger, which we will be just seeing after this. So, in electrical resistivity survey, a known current, as we have just discussed, here we take as I, is sent to the ground through a pair of current electrodes, which are in our case, in this example, in this schematic, are A and B. And the potential difference created in the medium by these rocks or formations, whichever is present, between another pair of potential electrodes, which are in our case, in our schematic, are M and N, and that is measured. Now, as I have just mentioned, that there are two known methods of arranging these electrodes, basically the distance between them and how they are arranged. So, one is the Wenner array, in which all electrodes will have the same distance, as you are seeing. The distance between all electrodes, whether current electrode or potential difference electrodes, will have the same distance A in all these cases. Whereas, in Schlumberger array, the distance is completely different. The distance between A and M is the same as B and N, but the distance between M and N is not same as A and M, as in case of Wenner. So, that is the major difference in it. There are advantages with one kind of array and disadvantages. So, that part we will be not going in deep, that is a typical geophysical prospecting or geophysical resistivity subject in more detail. So, commonly two types of electrode arrangements are made. One, as I have said, that the equidistance, that is the Wenner, the apparent resistivity is given. In this case, in the case of Wenner, apparent resistivity is given as rho A equal to 2 pi A delta V upon I. And here rho A is the apparent resistivity which we are trying to drive through or going to collect through M and N. A is the electrode spacing. In Wenner, all are having all A's or all distance between all electrodes are same, and delta V is the potential difference. And in case of Schlumberger array, the distance between, as we have seen, distance between potential electrodes is small, but compared to the distance between our current electrodes. So, potential electrodes difference is small and current electrodes is large. So, in this case, the equation would be the apparent resistivity is given by rho A, of course, equal to pi L by 2 power 2 and then B upon 2 power 2 divided by B multiplied by delta V and I. And here the almost same notations have been used here. So, delta is the apparent resistivity, L is the AB, that is the distance between current electrodes, B is the Mn, the distance between potential electrodes, A is the electrode spacing, and delta V is the potential difference. So, in which in two ways or through two different arrays methods, we can have the apparent resistivity measurement through such methods. Now, on what things apparent resistivity will depend? Of course, the distance between these electrodes, how they are arranged. Another important point, which very briefly earlier I have touched, is the longer the distance, deeper the layers involved in transmitting the current. But the signals which will come in these potential electrodes would be very little. So, one has to either amplify these things or do some other measurements or some other methods to that. So, generally there are optimization, not too much distance or not too short distance are done, because if we keep too short distance, then the signals will not go much deeper and you would not. Our ultimate aim is to find out the subsurface conditions and presence of water table, saturated zones and so on. So, distance has to be there, so that we can go quite deep, but not too much distance. So, there are two types of resistivity surveys, that is, one is profiling and lateral travelling. That means when we say profiling here, it means that we are going to have information along a line and a vertical section. So, that is what profiling, and we can move this line along a in the almost in the longitudinal direction and keep doing traversing, that is called lateral traversing. So, at one section, suppose 100 meter I have covered in one survey, then next 100 meter in the same line I would cover another. So, for whole area, suppose if it is 1 kilometer, then after doing 10 such profiling, I would get the idea about that area, but only along a line where the survey has been done. The other way we can do is the vertical electrical sounding or VES or depth probing, that is also is possible, in which we will be very briefly, just later I will discuss this one. So, first one is the profiling. So, the whole electrode array with fixed spacing is moved. The same arrangements, if I have chosen initially the Wenner array, then continuously for next section I would be doing the same. So, in profiling, the whole electrode array with fixed spacing is moved along a straight line, and apparent resistivity values for a more or less constant depth are measured. So, that whatever we will be measuring, if we keep the same distance arrangement, then we would be going through this on the same distance. Further, it is an important point here is along a straight line. If we go for in different directions, then the overall interpretation of that area would become very difficult and challenging. So, generally such surveys, electrical resistivity surveys, are done along a line or profile line. So, by this we are measuring apparent resistivity along the same profile line with different electrodes spacing. Laterals as well as vertical changes in apparent resistivity can be determined, and profiling this in first case has been used for delineation of vertical contact between bedrocks, between contrast or to find out the contrast in the resistivity characteristics of different formations or stratified formations, between bedrock, alluvium, steeply dipping formations, fault, dikes and saline. So, dipping formations also need not to be that we expect all the time that the layers or formations in subsurface would be completely horizontal. They might be dipping in one particular direction, and also faults. If there is fault, then in a small area also the formation might be dipping in two different opposite directions also. So, that kind of information can also be extracted through this profiling method of electrical resistivity. In case of vertical electrical surveys or methods BES, which is used to determine the depth of horizontal boundaries. So, that means we are going now to know about the extent of a formation or an aquifer, and in which the set of apparent resistivity values are obtained successively for different electrode spacing at the same location. So, suppose a 50 meter profiling has been done at one line, but now the movement of these electrodes would not be along the same line, it would move ahead. So, if a 50 meter area is there, then after a few such profiling we will have a complete idea about that area. So, that what I am trying to say, that in profiling method, when the electrodes are moving along the same line, then you are covering a large area, but in less details. Wherein VES method, you are covering a small area, but more details. So, again this this kind of judgment has to be made as per the requirements of water resources or groundwater exploration. If some areas are having real big problem of groundwater, then I would suggest then BES is much better. It will give you the complete idea about subsurface conditions, about aquifer, saturated zone, water table, fractured and weathered zone, all kind of information can be obtained. Now, as we can see that these are the one representative plot is here, which is showing the apparent resistivity, and it is showing through in a form of curve, and depth in meter is also shown, and there are what it is saying that different rocks will behave differently. So, here all of a sudden we are having different kind of rocks at that. This curve basically looking how this curve is representing how apparent resistivity is changing with depth. With depth, that is important. So, what we are having here that in this case resistivity with depth is increasing, but may not be in all cases. It might be a just reverse scenario also. So, the value of apparent resistivity here is plotted as a function of electrode spacing on a log paper, which will give you an electrical sounding curve. Now, there are softwares and other things are there, or software inbuilt the resistivity instruments or resistivity meters. So, these things can be done in the field very quickly, and all such facilities have become possible, but nonetheless one should understand what the instrument or computer is doing, which is with the and the software what it is doing, how it is estimating the depth and apparent resistivity. So, in simple case of a single homogeneous isotropic layer, it is theoretically it is fine that we will have a homogeneous isotropic layer, but in nature it is very difficult or impossible to find a single homogeneous isotropic layer. Anyway, just to understand things, we always start with simple case. So, in a single homogeneous isotropic layer of finite thickness or of infinite thickness, the plot for apparent resistivity versus electrode spacing would be a straight line. So, this line instead of a curve would be a straight line in case of a single homogeneous isotropic layer of infinite thickness, but we do not get, and therefore, we get the curve. So, that is one extreme, and the real one is shown through the curve. Now, here in this plot what we are seeing here, like here the drilling time, because drilling time, this is a subsurface information is already there. So, in case of drilling time, different rocks will have different drilling time, because some are hard, some are soft, and maybe just loose sediment. So, there the drill bit will go very quickly. So, drilling time versus lithology is plotted here, and then of course, it influences the resistivity, which is also discussed here. So, as number of layers or shown here, as number of layers increases like in A and B, and particularly in this section which you are seeing, interpretation becomes difficult and complex, because the resistivity, apparent resistivity will also change accordingly, and the curve may not be a very smooth curve, but a very have lot of kinks and other things. So, curve matching techniques or empirical methods have been evolved for obtaining bed thickness. So, not only because we are also looking what is the thickness of an aquifer or what is the thickness of a formation. So, through which we also we can find, and true densities of formations or resistivities, true resistivities of formation can also be found. So, in case of BES sounding, sounding have been successful in delineating depth to bedrock, saline water, fresh water interface. So, in coastal areas or in other areas, if you are having this situation, then BES is again very useful. Also, it can find out the contrast in apparent resistivity between weathered fracture rocks and hard rocks or consolidated rocks, and also it can find out the contrast in resistivity values in context of sedimentary rocks like clay and sand. The clay or clay stone and sandstone both are, these are the clay, and when we say clay and sand, we mean sediments. When we say clay stone and sandstone, we mean rocks. So, whether it is clay and sand or clay stone and sandstone, the resistivity contrast would be very high. The reason is, as we know that the clay sediments are very fine grained sediments, whereas sand sediments are relatively coarser sediment, and therefore, they will have, and there are more chances of. So, that the contrast through this electrical method, especially VES, can be detected very easily if the layers are arranged like this. So, appreciable resistivity contrast would be there, because we are also looking, because clay is not good from groundwater perspective, whereas sand is very good from groundwater. So, we are looking such contrast, because two clay layers and in the between you are having a sand, then that might be a confined aquifer conditions. So, alternate clay layer, sand layer sometimes are advantageous also. So, there are like in Indo-Gangetic plain, this is the situation also. Clay layers might be less thick or thin, whereas sand layers might be thick. This also depends on the size of sediments as well. So, there are several situations in which the results of interpretations may be inconclusive, and if it is the situation, then of course, we have to resort to further methods of surface geophysical exploration. But in what are the situations where we will get inconclusive? Some chances are there when thin layers in deeper levels will not be clearly identifiable. So, when we get thin layers like clay, and generally clay layers are thin relatively, then we will not be able to identify clearly in our data and through our surveys and suppression of adjacent layers. And secondly, water quality also influence results. We know salinity influence results. So, if there are pollutants, contaminations, that will also influence our results. So, that is kind of limitations of such methods. And the third one is for a given sounding or profiling curve, no single unique solution exists. Each location is unique, each subsurface condition is unique. So, therefore, common thing or single unique solution cannot be given. Now, we moving when we do not get even good results from VES or profiling or Wenner or Schlumberger, all these methods are not giving good results, good understanding about the area. Then we can resort to more advanced resistivity method, which is called electrical resistivity tomography or ERT, or also it is a electrical resistivity imaging. Now, in this what we are seeing here, first we will look this diagram and then we will see the other details also. So, this is based on the resistivity data, observed apparent resistivity data, and this is that kind of information you are getting, because there is no exploratory drilling is done, there are no boreholes available. Only through surface methods this kind of maximum this kind of information can be extracted. But when we do further processing, that is calculated apparent resistivity data, some improvements through certain models understanding can be done, but the data when it is being only collected on surface, this is what you get. And when you are having a resistivity contour sections, in case of ERT, when bore wells are there, here the data is coming from subsurface through this tomography, then you get a real good understanding picture along a line about that area, as you can see in the bottom figure. So, this that means the ERT or ERI, that is imaging techniques or tomographic techniques, are subsurface, they will give you information about subsurface structures, formations, and they know the basic fundamental is the same, that electrical resistivity will vary, and that is what it is measured, made at surface and by electrodes in one or more boreholes. This is important. Then only you get such kind of subsurface information. So, the information which is coming through these two boreholes in one place compared to what we get on through the surface methods. So, that is the advantage. Better understanding can be obtained through this tomography if we are having such a possibility of going some exploratory boreholes. So, if the electrodes are suspended in the boreholes, deeper section can be investigated, as we are seeing in the bottom figure. So, through exploratory drilling, sometimes when water has to be found in that area, these techniques basically initially developed for oil exploration, gas exploration, but now also these are becoming cost effective. So, people are also trying to employ in case of groundwater exploration as well. So, it is closely now I will give you analogy about ERT or tomography. So, you know, these techniques once it developed in one domain, very quickly we will see their applications in other domain as well. So, I am not going in the history that first it was developed in medical imaging technique or it was developed in oil industry and later on it went to imaging. That information I do not have and I do not want to discuss. What I am trying to say that the technique is also being used in medical sciences to do this kind of tomography to know about a human body deeper in organs, and if there are deformations or any other reasons to know about that. So, because in technique electrical impedance tomography, which is used in medical imaging, mathematically is the same inverse problem as in case of groundwater exploration or in case of typical electrical tomography. So, there is a analogy. This is the advantage in engineering or science, that any technique developed in one domain, the after few years you would see that the same technique in a little modified manner is being used in other domain. So, it might have been developed in oil industry, now it is also being used in medical sciences. So, in contrast to medical EIT or CRT and others, ERT is essentially a direct current method which is there. So, a related geophysical method also, which is induced polarization, or we say spectral induced polarization, is also there, which measures the transient response and aims to determine the subsurface chargeability properties. So, it is a different methods, variations in the different methods, which will give you which would detect basically transient response of this polarization and would give you information about the chargeability characteristics of different formations. So, finally, in this discussion we come to this electrical measurements can be, or electrical resistivity methods can be used to identification and quantification of depth of groundwater. As we said in the beginning, what we are looking? We are looking depth to water, we are looking the thickness, we are looking the density and so on, and also water saturation, salinity and detection of clays, again important from groundwater perspective, and measurements of groundwater conductivity. This is what we are looking, and this is what we will lot of information through such surveys which we will be getting through geophysical methods of groundwater exploration. So, this brings to end of this discussion. Thank you very much.